A 3-meter long ladder leans against a frictionless wall at an angle of 60 degrees. What is the minimum value of the coefficient of static friction with the ground that prevents the ladder from slipping? Okay, so this is a problem where we are balancing the forces and the torques. So we're going to start off with our givens and finds. So we're given L is equal to 3 meters. We're given an angle is equal to 60 degrees, and so we can see where that 60 degrees is, and that's it. And so we need to find US. Okay, so we're going to use the sum of the forces, and here, because we have forces in 2 dimensions, we need Newton's second law in both x and y. So we'll start with x. Some of the forces in the x direction are equal to 0. So what are the sum of the forces in the x direction? Well, I see N2 right here points to the right, so I'm going to start with that one since that's our typically positive direction. N2 minus the force of static friction, so Fs is equal to 0. And we also have the sum of the forces in the y direction equal to 0, and so those are N1 minus Fg equal to 0. Okay, so what don't we know? Well, we don't have any masses, but let's just write here N2 is equal to the force of static friction, and N1 is equal to the force of gravity, which is let's say um, the mass of the ladder times g. Okay, so we're good with the sum of the forces for a bit. Now let's do sum of the torques. So the sum of the torques, we don't want the ladder to rotate at all, so we want that to equal 0. We want to balance the torques just like we balance the forces. So we need to think about where we want our pivot point to be. Usually you pick a pivot point when you don't know one of the forces. So we don't know N2 and we don't know N1. But we also don't know the force of static friction. So I'm going to say that we want to pick this as our pivot point because then we don't have to know that information. So let's give that a try. So if I look at this as my pivot point, if I look down here at my pivot point, that force N2 would cause um, my ladder to rotate clockwise. So it would pull it over clockwise. So that's going to be negative. Whereas if I think about my force of gravity on the center of mass, right, that's going to cause this to rotate that way about the center of mass, and that's positive. So that's the one I'm going to start with. So I am going to write, let's see, so remember that torque is equal to R cross F. And so they show us here. Let's see if I can erase this for a second. They show us here in the picture that they give us they label something D, that D1. And so I'm going to use that. Just is giving me a good hint. That would be a good idea to use the R cross F, where I'm going to say this is equal to R perpendicular times F, and so I'm going to call that R perpendicular D. So that's going to be D1 times F. And so this is going to be my F of G. So I'm going to start with D1 times F of G minus D2 times N2 is equal to 0. Okay, and now if I want to find D2, my D2 is going to be, I know the distance from here to here is going to be L over 2. And so if this is L over 2, then D1 is just L over 2 times cosine of 60 degrees. So here I'm going to have L over 2 times cosine of 60 degrees times M times G. So that's the mass of the beam or the ladder times G minus, so D2 is going to be L sine theta. So L, so that's my L. And I'm going to use cosine theta. So cosine of 60 degrees. So if this is if this whole thing, let's erase this for just a second. This whole thing is L, right from there to there. That's my L. And then I'm looking for this right here. Then that's going to be, if this is my 60 degrees, then I'm going to say that's cosine of 60. And that's going to be times N2 is equal to 0. Actually, they have this marked. Let me just move this over for a second. They're using D2. I see why. So my D1 is incorrect. So I'm going to erase this. And we're looking for D2. And the reason is because we're looking for the component of R that is perpendicular to N1. And so notice when I picked D1 down here, I was picking this, the component here, but that's parallel to N2. I need the component perpendicular to N2. So that's going to be my D2. So therefore, if I need this component, then I'm going to need sine instead of cosine here. Okay, times N2. There we go. Okay, so if we want to solve for N2, then we can say, okay, this is L over 2 times mg cosine 60 is equal to L sine 60 degrees times N2. So we divide L sine 60 from both sides, and we get L over 2 mg cosine of 60 divided by L sine of 60 is equal to N2. And I can cancel my L's, and I get N2 is equal to mg over 2, and I'm going to have tangent. And so remember, sine over cosine is tangent, so I'm going to have tangent on the bottom. Okay, and so we know that here our N2 is equal to my Fs right here. So I'm going to say then Fs, I'm just plugging that in right here, right? So is equal to mg over 2 tan of 60. And I also know that that my Fs, let's see, and if I look back at my picture, I know that my N1 is going to be part of this Fs. So I'm going to have mu times N1 right is equal to mg over 2 tan 60. So here I know my N1, let's see, look back up here, is equal to mg. So I'm going to have mu, and this should be static, times mg is equal to mg over 2 tan 60. So I can cancel these out, and I'm left with mu s is equal to 1 over 2 tan of 60 degrees. So mu s then is going to equal 0.29. So that's the minimum value for the coefficient of static friction. This is the minimum value, so that ladder doesn't slip.